Okay. The dimension 2 case, simplest case, and so if we have here, downstairs here a vertex that belongs to L cubed. L cubed here. Then when you hyperbolize that, the metric around this vertex is given by that sigma L. So if L was 4, you wouldn't have any singularity. It's just a point space. And then you want to smooth that out by making L over 4 equal to 1. So eta is just, eta depends on R and D. It's just that function there for derivatives. Changing L over 4 to 1. Complex combination. L over 4 to 1. And then just smooth that out. So the new smoothed metric is hyperbolic inside the overlaid R minus B. And change here and outside with the old sigma N. So you have here singularity. And now let's see the case. Dimension 3 case. Okay, so suppose now we have a three-dimensional cube complex, and this is the hyperbolization of K. And remember, this is obtained by replacing the cubes here, the three-dimensional cubes, by a canonical three-dimensional hyperbolization. This is remember, a hyperbolic manifold with boundary and corners. So the picture is not as simple as in dimension 2, where you can draw this. Actually, if you take a pre-image of a two-dimensional face of the cube, you have this picture. So you have this picture repeated in every two-face pre-images. So the boundary of this is just made of a bunch of copies of this. Actually, the boundary of this is the hyperbolization. So the boundary is actually the hyperbolization of the boundary of the 3 cube. Anyway, so you take these three-dimensional cubes and you replace each cube by this three-dimensional hyperbolic manifold boundary. and anytime you glue 2 of them, you don't have any singularity. So in codimension 1 there is no singularity. It's like in here, if you glue 2 of these along a common side, there are no singularities here. The singularities only appear in codimension 2. And in codimension 2, well, you're in dimension 3, so you have segments there. And of course, if you glue downstairs here, you have a 1 cube is a segment, and you have that this cube belongs to 4 three-dimensional cubes, and there is no singularity there. It's like a paper model here, but the nice version of the paper model. So you multiply this by 0, 1, you are just doing 4 cubes, 1, 2, 3, 4. Everything is nice and Euclidean, and everything adds up. A cross section of this, of doing 4 cubes, is this model. But now suppose instead of having 4, you have the sigma L delta. You have this thing here, and you multiply this by 0. Of course, you cannot do that in 3 dimensions. If you try to put 6 cubes along a common edge in 3 dimensions, you cannot do it. You can do it in 4 dimensions like this, cross 0, 1. But you have a singularity here. Once you multiply this by 0, 1, you get a whole segment of singularities. But the singularity really is not a whole segment. It's in that the problem is not this direction. The problem is this direction. Now, when you go up, all this is Euclidean. When you go up, you are here in hyperbolic space. So it's not enough to just take this and cross by 0, 1. You cross by 0, 1, but to obtain at least piecewise hyperbolic pieces, you cross by 0, 1, but then you have to work. Because these things, okay, remember, go like that. So in the neighborhood of an edge in the hyperbolization, the metric is its form. So let E be an edge of the hyperbolization. Okay, it's a one-dimensional thing. Then the metric near E is, well, the cross-section. Remember, the cross-section is just forgot to mention. Suppose E belongs or is contained to exactly L cubes, L 3 cubes. Then the metric near the edge is, so you have the sigma L, which is the cross section, but then you have to work. So this is cosine this is just right here, the hyperbolic extension. Hyperbolic extension. Which is really just cosine hyperbolic R ds by u squared in R direction plus sigma. So it's not enough to take a product. In Euclidean case, you have to work by cosine. Well, anyway, now the idea is very simple. We know how to smooth this metric. We did it in dimension 2, right? We replace this by the GL, the one I just showed you before. This one here. We got the sigma L, and we replace it by the GL. We just change the eta by this number L over 4 by eta. And that's it. So if I want to smooth near the one edge, I take this instead of this. So I just replace it. So there is no problem here. The problem is here. So you just replace that by the GL. And then you get to smooth near the metric near. So this is really a two-dimensional case because the problem is in the cross section. Now this same method works in every codimension 2 in the codimension 2 cases. Because in codimension 2 the problem is in the cross section, and if you just move that out, then you get rid of all the singularities here. This is the method used by Gromov and Thurston for their branch cover examples. Because what they do is they take a hyperbolic manifold, they take a codimensional one manifold with boundary. I said n-dimensional hyperbolic manifold. they take a codimension 1 manifold with boundary, then they cut along this codimension 1, so you get something like this. Just cut along. And then say glue a bunch of these 2, 3, or whatever, another copy of this. And so you glue this side with this side, and this side with that side. Or you can do more than that. Then the metric is nice everywhere. If you glue this with that, then the metric is nice here. You're just doing locally two half hyperbolic spaces. The problem is here, where the length of a think of this as a circle here, the length in here is going to be like 2 pi, and then you continue here, and then you continue. Right, so you have singularity here of this one. And in general, this is dimension n, this is dimension n minus 1, this is dimension n minus 2. And this is going to be a big manifold, but the cross section is going to look like that. So that's how they do, they just smooth the two-dimensional thing, and everything is nice, and they smooth the metric, and that's how they got their example. Anyway, fine. So we can smooth the metric here. We can, and you do it for every edge leaving this point here. And so, well, so now is where the problems begin. So now you want to smooth around the vertices. First problem, this neighborhood is going to intersect that neighborhood over there. So this is nice as long as these two things don't intersect. So you want to begin smoothing the neighborhood of this, a big neighborhood, so that these two things don't touch. So that's not too bad. Okay, so this is not defined here, not defined here. Fine, but take a big rate. Fine. Okay. So what do we do now? And then the idea is to, well, now you can use the two-variable working tree, or the generalized variable joint tree. Remember, when you have a work metric, you can deform it to make it hyperbolic here and then extend everything. So, just apply the Charney-Jones or the two-variable working tree here and make it hyperbolic inside and smooth that metric. Well, that sounds very nice, but there are two problems here. And there are two problems. The first one is that the Faraday-Jones working tree works for work metrics. This metric does not work from here. Sine hyperbolic square, some metric on the sphere, plus dt squared. And then you ask yourself, is this metric work? I changed stuff here. Is this metric work? And this is not. That's bad news. So let me show you why this is not why this is not a work metric. So you have your big sphere here, and then you have it. And now, if this was, remember I said that when you have a work metric, the metric, so you have a metric G on the sphere, and then you work that by hyperbolic sine T squared. This is how a work metric looks like. So G is a metric on the in this case on the two sphere. So if you have like a curve here, the length of this curve will be equal to, so if this distance is this radius is t, this is the wall of radius t, then the length of this curve will be hyperbolic sine t times the length of the corresponding t, because everything gets to scale. So let's take, let's go to where the problem is. The problem is in this cube here. So let's take this circle here. then the length of this thing here, if I fix theta, the length of this thing here will be the length of something, for some metric g, times this distance here s. Sine hyperbolic of this distance here. I change t by s. So let's fix a theta here. And if this is t, remember in the two-dimensional case, and now I am in the two-dimensional case in the cross section because this circle is the intersection of this plane with the sphere. And in here I am in the GL case, and if this is t, then remember the metric like that. It is sigma L outside, hyperbolic inside, and in here it changes. And if this is t, the length of this is, remember, let me just write here, the metric GL is eta r minus b t squared sine hyperbolic t squared by dt squared. So that's a formula for the smoothed metric. I'm changing this stuff. So if this is t, then the length of this is 2 pi. Well, I forgot that. So the length of this is just 2 pi times this number. So the length of this circle here is, the length of that is 2 pi eta t sine hyperbolic. On the other hand, if this was work from here, let's fix theta, then as t changes, then this s changes. And that should be equal to some constant, which will be the length of this times sine hyperbolic s. Because it will be a fixed length that wouldn't depend on, it depends on theta, but it doesn't depend on t and s. It's big and big, very big. T changes, s changes, theta doesn't change. So when you scale, you get the same thing. So you need this equation here. Now, there is a relationship between t and s because they make an angle theta. So you have a hyperbolic triangle there. So you have here, this is theta, this is t, and this is s. So there is a relationship between these two. And you use the law of sines for, the hyperbolic law of sines, which says that sine theta is equal to sine hyperbolic t over sine hyperbolic s. That's the law of sines in this case because this is 90 degrees. So let me erase this. So from this you get that sine hyperbolic, you get a 2 pi eta t. So sine hyperbolic s is sine hyperbolic t over sine theta. So this is c times sine hyperbolic t over sine theta. So this cancels, and I get that eta is what is c over 2 pi sine theta. Right? Well, c is constant. It's the length of this fixed curve being expanded. Theta is fixed. I'm moving in this direction. So this is a constant. This is not a constant. Bad. not work. Oh, by the way, if eta is a constant, actually if eta is equal to 1, you get an inequality. Actually, you can go backwards and you get a proof of bits. So the fact that in hyperbolic space, in hyperbolic 3, in fact, the fact that hyperbolic 3 space is worked can be written like this: cosine hyperbolic r and h3. Well, minus 0 is also S2 cross 0 infinity work with sine hyperbolic t 0 plus infinity. So it's the same space. You can write it as work like that with the cross section, or you can write it as work from here with the spheres. It's the same space, right? That's how I got this. So if you go backwards, I'm just giving you a proof of the hyperbolic law of sines of this, using the fact that H3 can work in two ways. It's kind of interesting. Well, but let's go back to the argument here. So that eta is not constant. But again, use kind of that nice argument. Remember, eta is a number, is a function. This one. Eta is just changing between 1, the function 1, and then this is r minus b, and this is r, and the function L over 4. L over 4. I'm just changing 1 to L over 4. Then if I take t very big, this is not a, eta wouldn't be a constant, but you know, it will look like a constant. So just take t very, very big. And sure, this is not a constant, but it's going to change very slowly. So true is this, the metric, you know, the new metric with the changes I'm getting here is not warped, but if t is very big, at least locally it's going to look like this. So then you can deform the metric in some way. You have to do it very nicely so that all the rays get, you don't change too much things, and it is possible. And that metric, I call that method warp forcing. So you force the metric to be, a metric kind of close to be warped. I will have to define that and all that, but it is possible to do that. And whenever you get something that is close to being warped in a certain way, then you can make it work. That process is called, I call it, warp forcing. Well, so imagine you apply that, and then, well, you can assume that this is warping there. Just forget about the details. So now it's warped, and so now you apply the two-variable warping trick. Now it's a warp metric, and you smooth everything out. Another problem. Remember, for the metric to be close to -1 or at least negative figure, in the statement of the proposition here, you have two variables, a and b. The space you need to, you need lots of space to make these things with curvatures close to -1. They have to be big. How big they have to be depend on the metric, not of this one, but so this metric is hyperbolic sine of this distance of some metric here. These ones have to be well behaved because the A and D depend on this metric. So it might be that the metric I'm getting here after then I divide it by hyperbolic sine of this. The metrics I'm getting here are too wild, and the A and D I need are much bigger than this distance that I have. And you say, well, if the AD I have are too big, you can say, well, let's take this sphere bigger. But if you take the sphere bigger, then the metric is going to change too, because the metric here also changes. So you can keep taking bigger and bigger, but the AD that you get are getting bigger and even bigger and bigger. So that's a problem again. So there's a way to fix that. I don't have too much time. I wanted to talk about something else. So there's a way to do that, and the way you fix that is by fixing an angle theta. You have to fix an angle theta 0. And then here you have, this is R minus D, so this is kind of a cross section. This is R. once theta 0 is fixed, whenever I have an R, I have an S. So S is a function of R. And this is where I'm going to cut. This S here is going to depend on the R I choose here. And everything depends on this theta 0 that I fix. If I do that, you can use a nice argument like this one. I mean, it's not a proof, it's just a way of convincing yourself that this works. That you can prove that when the method you have from here is divided by this, and you take this R going to infinity, they kind of converge to some nice method. So in other words, if you do things in this way, the metrics that you get, they don't go wild. They kind of converge to something. So the AD that you get from the two working trip theorem, they will be bounded. They will be bounded because everything converges to some. These things only kind of converge to some fixed thing. So the AD of these things get closer to the AD of this thing in the middle, and in particular, they don't go to infinity. So I could take an R that is much bigger than that AD, say plus 1, and then I have all the room in the world to make the smooth. And yeah, it's not an optimal explanation, but and that's how you smooth things in here. Now, of course, what I said is not a proof. It's just nice heuristic arguments. And in fact, these are the arguments I had at the very beginning of the project that I used to convince myself that this is going to work. So the actual proofs are, I didn't prove anything really. But I introduced a few processes here. For example, the deformation make things work. That's work forcing that appears in the actual paper. The two variable warping trip appears, and so on. I mean, if you want to do things in dimension 4, then you multiply this by R. So this singularity now gets you some one-dimensional singularity. So once you solve this cross section, which is in dimension 3, then you have to work it by cosine again to solve the problem in this dimension 1, and then you keep some way. There are lots of problems that appear. You don't see the problem that one very important problem that doesn't appear here, but appears in dimension 4 and 5 is if you try to do this by neighborhoods of the faces, there is a lot of problem in the intersection. And you don't see that in here. Here it's very nice, but it doesn't. It's a very annoying problem. It happens a lot. Which is 4 and 5. Anyway, so that's kind of the geometric idea. Now, what I wanted to talk about the smoothing problem also. Now, if you see here, what I'm doing is working on this neighborhood, doing some tricks, some geometric tricks, constructions, and so on, working on this neighborhood. If you wanted to work in dimension 4, you will work on the neighborhood of this thing here, which is a three-dimensional stuff, cross here 1. So I'm working in every neighborhood, and all the things that I do are kind of, they preserve sections. And now if you have a cube complex, you have the hyperbolization of that, and then you want to take shards like that. That are nice products on the neighborhood. And why should I have a smooth structure that has such shards on the neighborhood of each face? And in general, you don't. And so that was a big problem. It's a global problem, and so let me explain a little bit about that. And I'm going to explain that in the here downstairs. Once you solve the problem downstairs, I'll tell you what the problem is, and then after much more, even more work, you can do it in here. But let me explain what the problem is. So this is, remember, this is the K cube, a little bit of notation. for the open K cube, this is the same square, doesn't matter the same square. 0, 1, K. Interior, if you have a subcube, of that, then the length, I'm going to use here the notion of geometric length. I mean, there are many ways of defining the length, but in this case, it is useful to, I just draw a picture here. So this is square L, this is the big one is square K, and then you choose a point X in the interior of L here, and you should choose an epsilon small positive, and you should from here segments that are perpendicular. So this is the X, and you should segments that are perpendicular to this cube at X and of left epsilon. Right, so and then take the endpoints. So you get an actual. curve. And if you're doing it here in the square, then you just take that's the length. Or here's the length. So if I need to specifically say this is the length, the epsilon length of square L inside square K at X. But in general, just ignore the X and ignore the X. I mean, the length also is defined as the unit vector to be solved, but I prefer in this case it's useful. All of them are equivalent. And then it's supposed to be a cube complex. A cube complex is something made of cubes, like initial complexes. And then suppose this is a square in K, then the length of the square in K is just a complex whose simplices are delta in delta prime, where the square is inside the square. So, for example, if K is this, and this is square, then you have the length of this in this cube, the length of this in this cube, the length of this in this cube, the length of this in that cube. This gives you a complex that's the length of this in the whole thing. Right? Right. Then I'll also use the notation delta for the canonical all-right spherical simplex. This is Sn intersection S1 Sn such that all xi are greater equal 0. So for example, delta 1 is that intersection with the first quadrant. Delta 2 is so this is the canonical all-right spherical and simplex. And a all-right spherical complex is just made of all-right spherical. And in particular, note that the length of delta of square K inside square L is this, delta L K minus. Right. For example, if this is square L, this is square K, then the length of this is that which is the spherical, all-right spherical. L minus K minus 1. And so in particular, this is an all-right spherical complex. There are spherical complexes, all of them with edge lengths equal to pi root. Okay, so now let K be a cubification or cubulation of a smooth manifold. So M, smooth manifold. And this is a smooth cubification of M. That means F is a homomorphism. And F restricted to each cube. It's like a smooth triangulation, just with cubes instead of triangles. F restricted to a cube. This is a cube in K. From the cube to M. M has a smooth structure. This is a smooth embedding. So if you, as I said, if you replace cube by triangles, you get the definition of the smooth triangulation. So this is smooth cubification or cubulation. And in particular, if you subdivide K, make it a simplicial complex, then you will get a smooth triangulation of M. And whenever you have a smooth triangulation, all the links of all simplices are PL spheres. So that means that, so in particular, the links of the cubes are PL spheres. So the link of any square inside K is just PL equivalent to the K, n dimension n, so this is n minus K minus 1. Should put PL equivalent there. So all the links are spheres. And then definition, a link smoothing of this. Okay. I know it's a PL equivalent, but it's just a homomorphism. A link smoothing of for some square in K is just a homomorphism from the sphere, like choosing coordinates to the length. Just choose any homomorphism. Now, of course, you have a smooth structure here. You can push forward a smooth structure and gives you a smooth structure here. That's why I call it a link smooth. Somehow you're smoothing this. But this is just an arbitrary homomorphism. Now, oh, I forgot to mention. Yeah, I forgot to mention here that so this is not me, right? Now I'm going back 5 minutes to explain something before that. So suppose you have a cube in here, and we are going to identify a neighborhood of the open cube with a cone of the length of this in K cross. So this is a canonical identification of the neighborhood of any cube inside K. And what is happening here is just imagine suppose you have this edge in the middle of the cube, and so the length is there's a circle there, but it has a neighborhood that is equal to what? You get a circle, which is the length. You cone that, the length is this. If you cone that, you get the star, the cone of the link is this. So this is the link. Here is the segment. Here is the segment. This one here. Here. So here's the segment. Here's the link. And then you smooth it. You cone that. You get like a disk. And you cross this by 0, 1. So you get a whole neighborhood. Filled solid cylinder here. So that's what I'm saying here. You identify a neighborhood of an open link with this, and this is the open link. You should probably do the open link. So I'm taking the open link. So this is open. This is like a cross section. The actual cross section is just the boundary of the cross section. The link across the. So now, whenever I have, now I go back to the future, and then whenever I have a link smoothing. Right? Now I have a map from the sphere to this. If I cone that map, I get a map from the actual disk, the real disk, to this. And then I can cross that with the open cube, and I have a map, kind of a chart of mapping on the neighborhood of this. So I write this. I define this as being the map that goes from the disk, dimensions here, n minus k cross qk to the cone of the link. Now this lives in k subset of k. It's just this neighborhood here. Now I have this is you can think of this as a subset of Rn. Open. This is open. This is the open disk. This notation. Maybe I should put it that way. So this is an open set of Rn, and I have just a nice homomorphism from here to a neighborhood of that. This is a very nice map because respect is essentially the identity on the second coordinate. So in respect, so it sends these rays just to these rays. It sends this direction to this direction. Very nice map. And in the hyperbolization thing, we want to work on charts. We want to work in here, so we would like to take a pre-image of that here and take all these directions. And these are, but even though I'm doing it for cubes, you would like to have it on the hyperbolization. This is the first step, to do it downstairs in the cubes. And these are very nice charts. They respect all the cube structure. So these normal directions are given by the cube structure. So I mean, rigorously, these things live in K. So rigorously, these things live in K. And M is here. So rigorously, probably I should, well, I actually didn't define it. So this is just the cone of the map of the link smoothing cross the identity of the K. And probably I should put the F here so that I go to M. This is in K, maybe I should. But you know, I'm just, from now on I just forget the function F. Just identify K with M. Anyway, so this is the, so this dn minus K cross, this is called a normal chart. It's normal with respect to K. So, because everything depends on the geometry of K, of the cubes. Right? So this is a normal chart. And if you have one of these for each cube, then you cover the whole K, the whole M. And then a collection L links moving, one for each cube in K, is called a set of link smoothings. And whenever you have a set of link smoothings, you get an atlas. This atlas depends on a collection of link smoothings, which is a collection of all H. Well, yes, I have to put that. Sometimes I just say, instead of saying this is a chart, I just say this is a chart. Just take a function of data. All right, so whenever you get a collection of link smoothings, you put the dot over there. Actually, here, it's a bullet. So whenever you have a link smoothing, you just count that cross with the base, you get a collection of charts. This is called a normal atlas. And of course, it's just there's no assumptions here, this is just a topological atlas. There's no reason why this should be a smooth atlas. Well, and but if this atlas is smooth, if the change of coordinates are smooth, then you get a smooth atlas. The very smooth atlas induces a smooth structure. So then if this is smooth, so if smooth, then we say that A is a smooth normal atlas. Smooth normal atlas. And it induces a smooth normal structure. And the smooth normal structure has charts that are this form. And this is what we want, at least, not just on K, but actually we want it upstairs, because we want to work in neighborhoods. And then, then you ask yourself, do I have such an atlas? Of course, you have to begin with something that is smoothable already. I haven't used the smooth structure here. I have used it only to get this fact that this is a sphere. Other than that, I haven't used the smooth structure. So that the question is, I begin with M, with some smooth structure, and the first question is, can I choose these link smoothings so that I get a smooth normal atlas for that smooth structure here, a given one? Right, so we are given some smooth structure here, and we have a cube relation. So there is a relationship between the cubes and M. All of them embedding M, so this is M, and the cubes. I mean, the cubes could be pretty bad. It's still smooth, but something like that. And then you have charts for this because this is smooth structure. So you do have charts that map that to some open set in Rn. It's a local diffeomorphism of some neighborhood. And then the cubes could be here really crazy. They don't have to be exactly like that. Anyway, so is it true that, in other words, is it true that the smooth structure here is a normal smooth structure? That is, it has charts that are smooth. It's not. It's not. There's no reason why it should be. And actually, you can find examples really simply are true that these things are not. You just move all the cubes really badly around the vertex. Anyway, so in general it's not, but then can I change it? Can I at least find one? I mean, I really don't care. I just want an atlas that is like that because then I can do the process chart case by case. And then the theorem says that so let F K be a smooth simplification of M. Then there is an L, a choice of link smoothings. You can choose this, they exist such that the smooth structure generated by L, so remember this L gives you an atlas, that atlas induces a structure, so of course it's just topological, this S induced by L is smooth, it's a smooth normal atlas. Moreover, this smooth structure is diffeomorphic. It's not equal, but it's diffeomorphic to the heterogeneous. over S M with the new normal structure is diffeomorphic to the original M. M came with a smooth structure. So you cannot expect the given smooth structure to be normal, but if you change it by a diffeomorphism, you can get it to be normal, so you are good to go and do all the stuff you want. So you can do that downstairs for the cubes. And then once you do that, remember you have a hyperbolization here. And the links downstairs are equal to the links upstairs. That's true for the Charney-Davis hyperbolization. Actually, it's true for all hyperbolizations. One of the big properties of hyperbolization is that it preserves links. That's how you do all wonderful stuff that you can do with hyperbolization. They preserve links. So you have, kind of a cube here, and then it has a link here. When you hyperbolize, instead of this, you have some kind of some hyperbolization stuff, but the link of it is the same. That's this. And because you glue the same stuff, you glue the same stuff. The pieces are different, but locally it's just the normal stuff is the same. So the links are the same. So now you can define normal chart in here as being the cone of that again. Instead of crossing with the cube, you cross with this hyperbolized face, and then you get normal stuff, and you want to do the same thing upstairs. And it's even harder to, you use the normal structures in here, you want to kind of move them back up here. And, it's doable. It's even harder than doing downstairs, even using the fact that you did it downstairs. But it's doable. You can do it upstairs also. So if this is a smooth structure, then you can change. Now, what you don't get upstairs here is that the final normal smooth structure is diffeomorphic to that. You don't get that. But you do get a normal smooth structure upstairs. Nice one. And then now you can do all the stuff, chart by chart, using these charts. And right, and to finish, I didn't have time to actually explain too much, but let me just to do the smoothing. Remember, you have a cube. Before doing this, one of the steps doing the smoothing of the metric, when you want to work on a neighborhood of a face, a problem on the neighborhood of a face, remember, is not really in this direction, in the direction of the face, it's in the direction of the cross-section. So what you want to do is first hyperbolize cones, because this direction is the link, and cone that, so you get the cone of a link here, and so one of the steps is to know how to smooth cones. And a hyperbolic cone is just a all-right spherical complex, homomorphic to the sphere, P homomorphic to the sphere, and what else? And you want to smooth that out. You are going to have a singularity here in the vertex and singularity in many places. And this is one of the steps. And I just want to show you that there are many, many constants that you need to do all this stuff. And for example, so you want to smooth cones. So you begin, I won't explain what that is, but you fix this constant, you fix some numbers. These are the D's from the AD. They come from each dimension of the cubes. So you have codimension 2, codimension 3, codimension. They appear a whole bunch of those D's. Whatever, DC, whatever. Some more constants. But here's probably what. This R up there is the R that I showed in dimension 3. The R and the D. That's that R. Everything will depend on R. This is a normal atlas on the sphere. This is just a diffeomorphism because these things are spheres. You need a diffeomorphism of the whole thing. Using all that information, canonically you can actually smooth the metric and construct. Canonically you can smooth the metric and construct a smooth metric on the cone of this PL sphere, P. So remember, these are the smoothings, these are the kind of global smoothing, this is the R, these are other stuff. And so given all that information, you can canonically construct a smooth metric in there, and you want the process to be canonical because the proof is by induction. First, you smooth all one synthesis, then you smooth all two syntheses using the fact that you have already smoothed all one synthesis. So you need a canonical process. And it depends on a bunch of variables. And
any questions?
Is there any control, like, say that you ask about the rank of the hyperbolized manifold? Is there any the rank or something? Is there any control you can get? Like for instance, can you say when you end up with one of the known examples, like the?
Well, I mean, you
almost never.
Well, it depends on what you begin with downstairs, right? Yeah, I mean, as I said, if you begin with something that has non-zero rational constraint classes, then you are not. If you don't, well, yeah, I don't know. Probably most of them are going to be named. Right? If I were to randomly choose 100, probably 99 of them are going to be named. That's my guess. It's probably true.
So I'm saying that you have this very nice thing where if you pull back along the projection map, if you inject some cohomology, at least given some assumption, is there any other information you can get about the?
Well, yeah, I don't know. It would depend on the specific problem. I mean, I don't know, some general theorem. And this question actually doesn't really. The question that you're asking doesn't really matter for the smoothing. Actually, it's a question just for the Charney-Davis hyperbolization. Yeah, I don't know. Just can ask me any questions.
This is a little tangential to what you're doing, but if you were to start with just a PL manifold, you weren't worried about smoothness, is there a natural way to get a cubulation?
If you get, yeah, because every sequence can be cubulated. Is that right? Cubulated. How do you do that?
Take the very center of the
Is that? 1, 2, 3, 4, 1, 2, 3, 4.
Okay, and then the intersections of the cubes are not a problem.
Yeah. Another one.
You just take all the very centers.
Now, comment that I forgot to mention. This works because I have a cubulation. I have squares here. If I do triangulation, I don't know how to do this. Probably it's not true. I don't know. For some reason, it works for cubes and it works for all right spherical synthesis. So this is an all right spherical complex. The proof works. This is a cube complex. The proof works. If I put triangle, it doesn't work.
But this is how you get the smooth cubulations here. You just use the triangulation theorem, and then you.
Well, I mean, you can do many things because I mean you can. The problem of hyperbolization, you begin with a simplicial complex, and then you apply the usual problem of hyperbolization or Davis-Lewis-Gibbs hyperbolization, and you get a cube complex, and then you do it again. So that's another way of doing it. And this way is nice because you get also that the links large. Or you can just take a triangulation and cubulate everything, and now you have a cubification of the space. Yeah, but it's very strange, and I guess using this you can prove some kind of stuff. For example, you can prove that kind of a nice proof that, of course, prove every PL manifold of dimension less or equal 7 is smooth. For example, you can use this. Actually, a part of the lemma of the proof. And for some reason, I mean, it was missed. When people were doing all this smoothing theory in the 60s or 70s. Maybe because they never started working with cubes.
Let's thank the speaker again.
We have a break now, be sure to notice that